Okay, so what we're going to look at in this video is the formula for variance, a little bit of motivation for it, and also we're going to look at deriving an alternative formula for variance, which might make some of our calculations a little easier. Okay, so suppose we've got two simple lists of numbers. The first list, -1 and 1, which I've got in blue here, and the second list is -1,000, 1,000, which I've got in red. So we can take the average of each of these lists of numbers. So the average of the blue list is 0. So -1 plus 1 is 0, and of course if you divide that by 2, then you still get 0. Okay, what about the average of -1,000 and 1,000? Well, you can see that the average for that is also 0. -1,000 plus 1,000 is 0, divided by 2, and you get 0. So the average for both of these numbers, both of these sets of numbers is 0. But we can see that the red set of numbers, or the red list of numbers, is far more spread out than the first list of numbers. So in the blue list, each number is only 1 unit away from the average, whereas in the second list, each number is 1,000 units away from the average. But they both have an average of 0, so clearly the average doesn't give us any indication as to how spread out the data is about the mean. Okay, so we need a way of measuring spread, a way of measuring how spread out the data is, because the average, whilst it might give us a value for some sort of central tendency, it doesn't really give us, well, it doesn't give us any information with regards to how those data points are distributed. So what we might be tempted to do is just take each number, and what we could do is we could subtract the average, and then maybe take the average of those values, possibly. So let's try a list of numbers 1, 3, 3, 7. Okay, so 1, 3, 3, and 7. We can take the average of these four numbers, which I'll call x bar. So x bar is just the sum of these four numbers, 1 plus 3 plus 3 plus 7, all divided by 4, which gives us 3.5. So I've put 3.5 in red there, just to remind us that this is the average of these four numbers, 3.5. So what I can do is I can go through the list, 1, 3, 3, 7, and subtract that average, 3.5, from each of the values. So 1 minus 3.5 is minus 2.5, which I've got in blue there. 3 minus 3.5 is minus 0.5. And again, 3 minus 3.5 is minus 0.5. And 7 minus 3.5 is 3.5. So I've subtracted the average from each of those numbers. And each time I've got the number on the right, which is the blue number. So what I could try and do is I could try and take the average of these blue numbers, which is just the difference between each data point and the average. And if I try and take the average of those differences, so the average of the blue numbers, we can see here that what I get is minus 2.5 plus minus 0.5 plus minus 0.5 plus 3.5 divided by 4, because there's 4 of them. But this gives me 0. So in some sense we're saying the average difference between each number and the average of the data is 0. But none of the numbers are exactly the average. There's always some difference between them. So it doesn't really make sense to say that the average of these differences is 0. Well, perhaps it might be the case that this was just a very poor choice of example. So let's have a think. Was this just a coincidence? Did it just happen that the numbers 1, 3, 3, and 7 didn't really work, or didn't it matter? Well, let's suppose now that we've got an arbitrary list of numbers, which I'm going to call x1 all the way up to xn. So x1, x2, x3, and so on up to xn. So we've got x numbers. And we can define the average, x bar, as 1 over n times the sum of all the numbers. So you can see I've started using sigma notation here to denote a sum. So what we're going to assume in this video is that you're comfortable with sigma notation and the properties of this sigma notation, namely that it's linear. Okay, so let's consider the expression 1 over n times the sum with I running from 1 to n of xi minus x bar. So what we're doing here is we're just taking each data point, we're subtracting x bar, we're adding up those values, and we're dividing by n, the number of data points. So this is exactly what we did with the numbers 1, 3, 3, 7, but this is just in a more general form. Okay. So what I can do is I can distribute that sum. So what I've done here is I've highlighted the first part in blue and the second sum in red. So again, if you're not comfortable with going from the first line there to the second line, it might be worth reviewing the properties of sigma notation, just so that you're a little bit more comfortable with what's going on here. But hopefully that should be okay. Okay, we're just distributing that sum. Now if you look at the expression in blue, that is 1 over n times the sum I running from 1 to n of xi. That is exactly the expression for x bar. So on the line below, you can see that I've replaced that blue sum, including the 1 over n, with x bar, because those two expressions are the same. Now if we look at the expression in red on that second line, we can see that that is the sum I running from 1 to n of x bar. But x bar does not depend on I. So we're literally just adding x bar to itself n times. So the result of that sum in red is n times x bar. But of course we've got a 1 over n out the front. So in total what we've got is x bar minus 1 over n, lots of n x bar. So you can see straight away that the 1 over n and the n are going to cancel in that second term. So we're going to have x bar minus x bar, which is 0. But this was done on an arbitrary list of numbers, x1 up to xn. I didn't place any restrictions at all on what those numbers could be. Yet by taking the average of the differences, I get 0 no matter what. So the previous example wasn't a coincidence at all. It will always turn out to be 0. And clearly this is not satisfactory. So we need to go back to the drawing board. We need to come up with an alternative approach. One alternative approach is to take the difference between each data point and the average as before, only this time we'll square the result. So we will square the result. What this will do is this will give us a list of positive numbers, or perhaps a list of non-negative numbers, we should say, because there is the possibility that some of those terms might be 0. But certainly if any of the xi's are different from the average, then this expression will be strictly positive. So we're going to define sigma squared, little sigma squared on the left hand side, to be equal to 1 over n times the sum I running from 1 to n of xi minus x bar squared. Okay, so we're squaring those differences, then we're adding them up, and then we're dividing by n. And we're going to call this sigma squared. And this expression, this quantity, is known as the variance of the data set. Notice that the expression on the left, sigma squared, little sigma squared, we are treating as a single symbol. Okay, so we're not thinking of it as sigma, some quantity sigma that we're squaring. Sigma squared is the entire symbol, okay, and it is the variance of the data set. Okay, as I mentioned before, it's clear that sigma squared is greater than or equal to 0. It's the sum of squares. Okay, we're dividing by n, but that's not going to change the sign of the expression. And perhaps more importantly, the variance is equal to 0 precisely when each data point is exactly equal to the average. Okay, which would make sense, right? Because if each data point was equal to the average, then there would be no variation at all. There would be no spread. Each point would be exactly sitting on that average point. All it takes is one data point to be different from the average. The difference will be non-zero. When we square it, we get a positive number, and so the sum will be strictly positive. So at the very least, this is starting to look better, because we won't always get 0. So we will only get 0 when each data point is equal to the average. Okay, so this quantity variance is a way of measuring spread. There are other ways. We could have, for example, taken the absolute value of the differences. But this particular way of measuring spread is called the variance. Now what we're going to look at is how to derive an alternative formula for this expression. So how can we derive an alternative formula for this expression? A perfectly valid question might be, well, why would we want to? And it turns out that I think this second formula is slightly easier to remember. There's a nice little mnemonic, which I'll tell you at the end. And also it actually does result in fewer calculations. And so fewer calculations means less room for error, which is always something that we can or we should strive for. Okay, so deriving an alternative formula. So we have our expression. The variance, sigma squared, is equal to 1 over n times the sum I from 1 to n of xi minus x bar all squared. Now there isn't really much we can do with this expression except perhaps square the bracket xi minus x bar. If we square that bracket, we get, still inside the sum, xi squared minus 2 times x bar times xi plus x bar squared. Okay, so we're just foiling out that bracket, still inside the summation notation, and we get that expression there. Then what we can do is exactly the same as what we did before. We can distribute that sum to get this third expression here. Okay, so we get 1 over n, sum going from 1 to n of xi squared, minus, remember that the sigma notation is linear, so we can distribute that 1 over n as well. So we get minus 1 over n times sum I running from 1 to n of 2x bar times xi plus 1 over n times the sum I running from 1 to n of x bar squared. So all we've done is we've just distributed that sum across those three terms. Okay, so again we're using the properties of sigma notation. Okay, so it's looking maybe a bit scary at the moment, and it doesn't look as if it's perhaps any simpler than what it was before. In fact, it looks considerably nastier. It's all going to work out, so let's see if it does. Okay, so on the next slide we've got 1 over n times the sum I running from 1 to n xi squared minus, and what I've done here is I've taken that 2x bar, I've taken it outside the sum. So this second sum I've now highlighted in red, and I've taken that 2x bar outside. That's because you can take out any constants from the sum. Okay, you can factorize them out. And that is exactly what you're doing. You're factorizing, effectively, because that sigma notation just represents a sum. Anything that depends on I, the running index, must stay inside the sum, but 2x bar doesn't, so we can bring that outside. Plus, and then I've got 1 over n, and then I've got the sum, I running from 1 to n, of x bar squared, which I've highlighted in blue there, and we'll see why that is in a second. Okay, now we might wonder why I highlighted that middle sum in red, and it's because, once again, that is exactly the expression of the average. That is x bar, 1 over n times the sum I running from 1 to n of xi. That is x bar. So on this second line, we can see that this is equal to 1 over n times the sum I running from 1 to n xi squared, not much we can do with that really, minus 2x bar times x bar in red there, plus 1 over n, and now we get to the blue expression, and we're going to use the same kind of thinking that we did previously. Namely, we've got the sum I running from 1 to n of x bar squared, but x bar squared doesn't depend on I, so you're just adding x bar squared to itself n times. So that blue expression there is nothing but n times x bar squared, which you can see I've highlighted in blue in the second line. So what have we got? So we've got 1 over n times the sum I running from 1 to n xi squared. Again, not much we can do with that. Minus 2 times x bar times x bar. So that's minus 2x bar squared. Plus, and then we've got 1 over n times n x bar squared. Now clearly, the 1 over n and the n are going to cancel. So we're just going to have plus x bar squared. So we've got those last two terms, minus 2x bar squared plus x bar squared. So in total, that is minus x bar squared. So what have we got? Our final alternative formula is 1 over n times the sum I running from 1 to n xi squared of xi squared minus x bar squared. And the way I like to remember this formula is it is the average of the squares minus the square of the average. So this is the average of the squares minus the square of the average. So you square all the data points, you find the average of those new numbers, and you subtract off the square of the average of the data points. So it's the average of the squares minus the square of the average. This is useful because it will also allow us to remember the formula for variance of discrete random variables and continuous random variables. Okay, a very similar formula will work there as well. Okay, so average of the squares minus the square of the average. Okay, thanks.